Okay, thank you very much. This has been a great meeting. Lots of info about new FRBs and so forth. And so I'm going to talk about some aspects of propagation effects. This is not all about propagation effects. So I'll talk about some of the basics, but two of the themes I want to focus on are the impact on surveys. In other words, are there selection effects that come into play from propagation, like scintillation boosts or diminishing, that kind of thing. And then also turning it around and using measurements of FRBs to learn something about the media anywhere between us and the source. And for me, that especially means the host galaxy. So I guess my pointer doesn't really show up. But anyway, HG here means host galaxy. And then I'll end, in due course. And then I'll end with some questions about things. So anyway, just for starters, it's very clear that if you look at the distribution of dispersion measures and scattering time, so by scattering time I mean the tail on the pulse, when you see that asymmetry of the pulse, we call it the pulse broadening time. Anyway, if you compare FRB measurements, which are the open circles on both of those frames, with galactic pulsars, against galactic latitude, you see a distinct, it's very clear that there's extra dispersion, there's extra scattering from outside the galaxy. And then the question is where? Well, the answer, I would say, is, and I think we all know, is that there's dispersion in the host galaxy, or in a host galaxy, in the IGM and in the Milky Way, and maybe perhaps in an intervening galaxy in some cases. Scattering, however, I would say is either from the Milky Way or from a host galaxy, and not the IGM. At least that's my bet. Okay, so part of the, I'd say the program is to take the various measures that we have and unravel them into their components. And so that goes for DM and RM that we've talked about quite a bit. We haven't really said much about the emission measure or the scattering measure, but all four of these involve the electron density. RM involves the magnetic field, EM involves the electron density squared, SM involves the square of the fluctuating part of the electron density. So we basically want to break down each of these into the host galaxy, IGM, and Milky Way components where appropriate. And so for the Milky Way part, an electron density model is always a good thing to have. I'm not going to dwell on this very much because we could really get into the weeds on some of this. I will say a few things about them, but basically you can use what you learned from pulsars to construct a model, and then you can use that as part of this deconstruction. And same thing with a galactic magnetic field model in the case of RMs. You want to analyze the foreground. So I would say, I think this is still the only FRB where this has been done, but in 121102 and Tendulkar et al., the Balmer lines were measured from the host galaxy. That gives you an emission measure, which can then be used in a model-dependent way to calculate the host galaxy dispersion measure, or at least the portion of it that's along the line of sight. And anyway, the answer then ends up that in terms of DM, there are roughly equal contributions from the Milky Way, IGM, and host galaxy. But anyway, that's the program, and I think it's going to be hard to do Balmer line measurements on a big sample, but it would be great if that was done. Okay, so I also want to put this in the context of, let's say, the Magnetar model in broad terms. So we've seen this picture a lot, and there are different flavors of Magnetar models, as we heard. And basically, the central engine is here, but in those models, the bursts are actually produced in the forward or the reverse shock and that type of thing. But I kind of want to give a bigger role to the central engine. So I've put in a familiar-looking cartoon here, and then I've also put in the propagation media over there. And so one question I have is, maybe the central engine is the thing that's producing the bursts, and then the circum-source region is, maybe it's also producing bursts some of the time, but it also becomes a propagation medium as well. So one thing I wonder is, for example, can the synchrotron masers, I mean, laboratory masers are used as amplifiers, right? And interstellar masers amplify background sources. So perhaps these kinds of masers can also amplify bursts coming from the central engine. How might that be? Well, you have to open up propagation paths through this fairly dense region, and maybe the energy coming from such an object, the flares and so forth, can just tunnel through in some sense. So that's a question, really. It's not an assertion. Okay, so in terms of propagation effects, we're all familiar with refraction, diffraction, and caustics. The bent pencil, of course, diffraction from a single slit, or viewed diffraction of a point source through a screen, and then caustics, where you have especially bright patches of light, bottom of a swimming pool or from a glass and so forth. So that's what we have. And then in terms of astronomy, we see the same effects. We see refraction in the form of refractive scintillation of AGNs. So these are so-called intraday variables. That's due to refractive scintillation in the Milky Way. We see diffraction, which gives multipath. That produces constructive and destructive interference. So we see scintillations in time and frequency. So this is a time frequency plot from nanograv measurements, monitoring of millisecond pulsars. The bright red there is an incredibly bright so-called scintille, or it's sort of a speckle, if you like. And that can come and go. And so the dynamic range of amplitude here, blue is very dim, red is very bright. That dynamic range can be 10 or 100 or even 1,000. Then we also see, if the scattering is bigger, we see the exponential-like tail on a pulse like so. So that's diffractive scintillation. That does occur in the Milky Way. We see it. It's ubiquitous. I would say it's also happening in any host galaxy to varying degrees. And then we also see caustics from things that are sort of like Gaussian lenses that produce things like the so-called extreme scattering events. But I would say it's not scattering in the sense of the word I would use. It's refraction with caustics. Okay, so we have that. And then in terms of diffraction, just very quickly, you can view a point source through a scattering screen, let's say a phase-changing screen that's turbulent. And then downstream, you see constructive and destructive interference as a function of x and y, so in some observer plane, and then versus frequency as well. And so these scintilles for a standard pulsar are about the size of the Earth. And then as we move and as the overall geometry changes, we see temporal variations. So that's the basic picture. So now what do we know about I'm calling it turbulence in the interstellar medium? So there's the so-called grand power law in the sky, which people have talked about for a long time. So a paper by Armstrong et al., and then more recently, Lee and Lee had just a year ago, had a very nice paper in Nature that connected Voyager measurements with pulsar measurements, basically, and a few others. And so this is a different well, in the past, what people have emphasized is the fact that the slope there seems to be 11/3, which is Kolmogorov. It's supposed to excite you, it's supposed to ring a bell. But what I'm emphasizing is that, and if you notice the scale here on the y-axis, that's a lot of orders of magnitude. So you can hide a lot of departures from Kolmogorov, in this. And so what I've chosen, well, I've put pulsar lines of sight here, pulsar measurements, scattering measurements, and so forth, but also dispersion measure variations with epoch. That's a 10-year time series. And you can put that together and you can look at different lines of sight. And you see that there are many orders of magnitude differences in the coefficients. So I should emphasize the spectrum there is, we often write as Cn squared times wave number to the minus beta, where beta would be 11/3 if it's Kolmogorov. And then the scattering measure is the line of sight integral of that coefficient, Cn squared. Oh, that's a spectrum. It's beyond the heliopause. It's actually measuring the plasma oscillations. And so that spectral line is telling you what the plasma frequency is. And so you get the density from that. So anyway, so I would say this is Kolmogorov-like. But what's not known, certainly not a priori, is what the inner scale is. That is, what's the maximum wave number. And so the Voyager measurements seem to indicate an excess at very small scales. And so these funny colored boxes here indicate the Voyager measurements on different scales. We also have some measurements here from monitoring the bow shock of this pulsar. So as it's moved, the nose of the bow shock changes because the density is changing that it's plowing through. So that gives us other points here. Anyway, what I've indicated on here, well, I think the main takeaway here is we have a broad spectrum of scales. And then those scales span across what the Fresnel scale is here. That's 10 to the 9 meters. So at smaller scales, higher wave numbers, those scales produce diffraction. Smaller scales produce refraction. So we're going to get both, and we see both. Okay, so anyway, so what do we know? Well, broad range of scales. It's Kolmogorov-like. There's also evidence that there's additional structure on AU and tens of AU type scales that seems to be different from the Kolmogorov spectrum. It's consistent, at least for some parts of the Milky Way, with delta n over n being 1, so it's highly modulated. So the spectrum has lots of fluctuations in it. And there's also evidence that there's accompanying magnetic turbulence, or probably we should say that the density fluctuations accompany the magnetic turbulence, because the magnetic turbulence is probably the dog, and delta n is the tail of the dog. Anisotropies. So when I say anisotropy, I mean the small fluctuations that scatter seem to be anisotropic. They're not circular, they're elongated typically. And I'll show a couple of examples of that. That's for some cases, but in other cases, it does look isotropic. And I say here, this is not inconsistent with the 2D turbulence model that Sridhar and Goldreich presented more than 20 years ago now. Galactic distribution, well, what's interesting about the Voyager measurements, which are still ongoing, is that they are more or less consistent with what we see from measurements along kiloparsec and longer path lengths. So we have a project that we've proposed. So there was a graduate student at Cornell who's going to continue to work with the Voyager data, because it probably has another 3 years at least of lifetime and still sampling the local ISM. But I also want to emphasize that as you look towards the inner galaxy, Cn squared goes way up. And as you go outside the solar circle, it goes down. And I think that's relevant for interpreting lines of sight to FRBs that sort of graze other galaxies. Okay, so here's an example of the information you can pull out of pulsar measurements. So these are dynamic spectra here at 3 different frequencies. So 1400 megahertz, 430, 300 or so. And all of this structure here is from diffractive scattering and scintillation. And the fluctuations here are 100%. So delta intensity over intensity is 100%. So anyway, so what's interesting, and I should also say these are not simultaneous measurements, but it doesn't matter statistically. The scaling with RF follows statistically what we expect. But what's remarkable is when you take the 2-dimensional power spectrum of each of these frames, you get these frames. And what stands out are these parabolas, this parabolic structure. And it's perfectly understandable, and I'll show you why I say that. But what's interesting is that a given parabola here, it'll look especially thin and narrow and prominent if you have a single scattering screen along the line of sight. It's the power spectrum of this. And so the color scale is just the amplitude of that power spectrum. These coordinates are the Fourier conjugate variables of time and frequency. Okay. So anyway, there are objects where you see multiple arcs, and that corresponds to a series of narrow screens along the line of sight. So that's reasonably interesting, and that's for nearby objects. So presumably the galaxy is filled with these narrow sheets due to processes we don't quite know, but we can guess. So I wanted to indicate that this is a generic thing, these parabolas, because you can take the old familiar single slit and the diffraction pattern, but so up in the top right corner there, you see the standard thing. That's in the far field, but if you evaluate the diffraction pattern at different frequencies, and then again color code the amplitude, this is what you get. So that there is a slice across here. So the x-coordinate here is a spatial scale. This is frequency, basically, normalized. And if you take the 2D power spectrum of this, you get this. So the parabola is a natural thing that comes out of diffraction. And I won't go into the details, but it's almost trivial why it's a parabola. But I won't spend time on that. But anyway, the point, so even though it's generic, the details of that parabolic structure, like how filled in this is, so here green means fairly bright and blue dim, and you see other structure here, but the detailed structure there tells you about the details of the medium. So the curvature here tells you about how far away the screen is, or in this case, the mask, and the sharpness tells you how thin that screen is, and so forth. And so that's what people have been using. You can't really apply this to FRBs because, well, going back to this, this is over about 40 minutes of time, continuous sampling. We don't get that with FRBs. But perhaps there will be an FRB where we get lots of them in an hour, and we might be able to do something like this. Okay, this slide is just to emphasize that our interstellar medium is incredibly messy, clouds and chimneys and so forth. That's just in the nearest 500 parsecs. And even our local cosmological region is similarly messy in terms of the distribution of galaxies. And we're looking through that when we look at FRBs. So I think interpreting measurements, going forward it's going to have to deal with some of this complexity, hopefully not all of it. All right, so galactic scintillation. Basically, any extragalactic source that's a point source, I mean a genuine point source, let's say a neutron star magnetosphere or something like that. Certainly if you look out of the galactic plane, it will be 100% modulated by scintillation. And the distribution of amplitudes is exponential, and so that long exponential tail can play a role in surveys. So the cartoon there that I have on the right indicates that any two FRBs along exactly the same line of sight would scintillate identically. But that's not going to happen because if their directions differ by even a micro arc second, their scintillations will be decorrelated. The other thing about that is that, of course, the FRBs emit spherical waves, but by the time they get to the Milky Way, they look like plane waves, and so they scatter differently from, say, a pulsar that sees the same medium that itself is emitting spherical waves. So it basically takes more scattering to bend a spherical wave than it does to bend a plane wave. And so in interpreting scattering from FRBs, you have to take that into account. Okay, so anyway, host galaxies should show completely analogous effects. Okay, so here is the hockey stick diagram. It's basically the scattering time versus dispersion measure. So the red here is based on galactic pulsars. And the hockey stick, the bend here comes about because we see lots of scattering when we look towards the inner galaxy, and less so when we look towards the outer galaxy and in the local interstellar medium, on a per dispersion measure basis. FRBs are shown here, upper limits, open circles, the black are actual measurements. And as I think Vicky showed a different version of this, basically, but the FRBs seem to be underscattered, at least with respect to this diagram. You can fix that by saying, this is the total dispersion measure. So if you say, okay, the IGM is contributing, and if it doesn't scatter, then all these points would shift to the left. And so you might be able to make, it hasn't been done yet, but you might be able to make the host galaxy scattering consistent with the hockey stick diagram for galactic pulsars. And that would say that the turbulence is more or less the same. And that might not be a big surprise, but if it does take special regions to produce FRBs, certainly the first repeater indicated that, maybe not so much now, then it would be interesting to know that we have the same kind of turbulence. Okay, so what can you do with FRBs? So for those FRBs where you see the scattering tail, the shape of the scattering tells you about the wave number spectrum and the inner scale, so the wave number cutoff. So so oftentimes most people talk about the exponential pulse broadening function that can get deconvolved from a measured pulse. And so people call those FRBs, fast rise exponential decay. And indeed, if you have a truly thin screen that scatters, you will get an immediate rise and then a decay. However, if the screen is thick, or if you have two screens, then you'll get a more rounded sort of thing. So basically, the rise time and the shape near the rise tells you something about the thickness of the medium. So here's a trivial example. If you have two screens that each would produce an exponential pulse broadening function, basically the net function is the convolution of those two, and you get a rounded feature like so. And so we know from pulsar measurements that we see both FRBs and SREDs, I guess. So like in the case of this heavily scattered pulsar, if you deconvolve the exponential, the fast rise, the FRED, you get the deconvolved pulse shape like here. That doesn't really look that plausible for a pulsar. But if you use the slow rise version, then you get a nice double pulse here that looks reasonable. And so here's the rounded pulse broadening function. So anyway, that's the type of thing that can be done. As far as I know, it has not yet been done. And then lastly here is a great example for a heavily scattered pulsar, a detailed study by Rickett et al., where they studied the roll-off here as well as the rise, and they concluded that the inner scale is of order 100 kilometers for that particular line of sight, which has an H2 region along it that this pulsar is viewed through. So anyway, I think the program could certainly include a detailed study of burst shapes and doing something along these lines. Now, I think that the sad trombone structure will confound this at least a little bit. So we'll see how well it works. All right, then anisotropy. So the way this works also is that you can infer something from the pulse broadening function. So I'm showing in the top row there the scattered images for different degrees of anisotropy of the scattering, going from circular to highly elliptical, and the pulse broadening functions go accordingly. So circular, you get lots of long delays, but as you go to a skinny, highly elliptical image, then you have many fewer long delays. So you have a much more compressed pulse broadening function like that for a high axial ratio. So just as an example of high anisotropy was this very beautiful analysis by Briskin et al. So here's the secondary spectrum here, where you see the overall large parabola, and then also these inverted parabolas that indicate substructure. And when so the analysis that can be done, you can convert this secondary spectrum into the effective image that is seen, the scattered image. And this is what the scattered image looks like. Milliarc second or tens of milliarc second scale here in right ascension and declination. And so the scattered image is highly elongated here. I forget what the axial ratio is, but it's clearly large. And then secondly, there's another scattering patch. So the medium that's doing the scattering is very patchy. Okay, so let's talk about detection issues. So if scintillations can boost up the signal, they can also diminish the signal. Lensing, either gravitational or plasma, can boost up the signal. I'm not going to talk about gravitational, but I'll say a little bit about plasma lensing. So anyway, if you have those boosts and diminishments, then that will clearly have some effect on surveys, but how big of an effect, I think we don't quite know. So anyway, FRBs are intrinsically compact enough to show diffractive scintillation, but if they are scattered in their host galaxies, that can squelch the scintillations from the Milky Way. So you can turn that around as well. And if you do see galactic scintillation and you see evidence of host galaxy scattering, you can determine where the scattering region is, or at least you can constrain it. And then the last point here is if this kind of selection effect is important, then there will be a very strong galactic latitude dependence of that. So anyway, here we have this is the amplitude distribution of the scintillation gain or amplification, if you want to call it that. As I said, it's exponential, so it doesn't fall off all that quickly, certainly not compared to a Gaussian. And if you're doing a lot of statistical trials, then you will be sampling this tail. So you can get scintillation boosts of a factor of 10 quite easily. But again, depending on how many statistical trials you're doing. What does that mean? Well, if you do a survey and you detect, say, 20 FRBs, like in the ASCAP survey, you have to ask the question, well, how many FRBs fired off bursts in those fields of view at the same observation times that were not seen because they weren't boosted up, or they might have been boosted down. The boost down is this point here. The most probable value is 0 amplification. The mean is 1, and then you have the long tail. So if you put this together with a luminosity distribution, now this is a luminosity distribution for bursts from a single source, power law with cutoffs in red here, then depending on whether you have fully developed scintillation, so DOF here means degrees of freedom, so the bare scintillations are 2 degrees of freedom, and you get scintillated curves here, so you have much lower luminosities. You also have boosts up here. So now you can ask the question, like when a survey is done, are we only seeing the tip of the iceberg, these high luminosity bursts? That might be the case for the most distant objects that have been detected. For the nearby objects, we're probably sampling over here where the scintillations really don't matter. And in that case, so there may be quite a difference between the low Z and the high Z or higher Z objects. Okay, so so what affects the degree of scintillations? Well, I mentioned source size, and I'll say a little bit more about that in a second, but another is bandwidth averaging. So the scintillations have a characteristic bandwidth. So across your band, it's a stochastic process with some frequency scale, and that frequency scale is given here as a function of galactic latitude. So it's if you go to 3 gigahertz, it's hundreds of megahertz. So if you have 100 megahertz bandwidth or even a gigahertz bandwidth, you're not really averaging out the scintillations. But if you go to lower frequencies, and especially if you go to lower latitudes, the scintillation bandwidth plummets. It becomes kilohertz instead of hundreds of megahertz. And there you're squelching you're just averaging out the scintillations. So if scintillations are needed to detect some bursts, this effect will go away because of this effect. So similarly, a finite source size, as you would get from a scattered FRB, does essentially the same thing. So it boils down to this. Let's suppose we have an extragalactic source here that's compact. It's emitting nice wave fronts and that reach the Milky Way. The coherence, well, and let's say it's compact but finite in size, so the coherence length of the radiation is the wavelength divided by that angular size. So from the point of view of the Milky Way scattering medium, that wavefront will be sufficiently coherent if that coherence length is bigger than the patch of the screen that contributes to the measurements by an observer here. So an observer sees multipath, so sees a range of angles. We're talking about a milli-arc second or something like that, typically. And so at a kiloparsec, that's it's an AU or so across here. So if the coherence length is bigger than an AU, then you will see the full scintillations. But if the coherence length is smaller, then you'll start squelching the scintillations. So anyway, that squelching can happen if you have the two-screen case or two-medium case. So here's an extragalactic screen in a host galaxy, let's say, and here's the galactic screen. So scattering here can reduce the coherence length. Okay, and anyway, you can work out the requirements for seeing diffractive scintillations from the Milky Way, and it involves, you can either think of it in terms of what is the effective angular size of the extragalactic source and also the scattering produced by the galaxy, or you can view it in terms of the pulse broadening time. So anyway, that's in the slides, and I'm not going to explain that, but I'm just saying that there is a criterion here. So now, so what is, how critical, what is the critical angular size for this coherence length effect? It's basically the planets don't twinkle, stars do effect. That's all it is. But anyway, the isoplanatic scale is sub-micro arcsecond here. And that's the typical scale here. And then versus galactic latitude and longitude, it's much more forgiving at high latitudes, and it's very unforgiving at low latitudes. So again, you would see this effect plus the bandwidth averaging effect could induce a galactic latitude dependence of FRB detections. Now, some years ago, it seemed like there was pretty good evidence that there was a latitude dependence, but these days, I'm not so sure. But anyway, this can be, so if we don't see it, then that will tell us something about the population and the role of boosts. So let's see, I guess I'm at the 30-minute mark?
Yeah, I think we want to leave 10 minutes.
Yeah, if I can say a bit, I'll breeze through the last slides here. Okay, so anyway, here's a cartoon model of this. So I've set up a population of burst sources that are not seen if there's no scintillation. They're too weak. And anyway, this is showing the number counts of detections against latitude and longitude, and essentially no detections looking towards the center of the galaxy, but lots at high latitudes. So that's the effect. But again, I don't think scintillations are always required to see bursts. That would be, I think that's inconsistent with what's been seen now. But nonetheless, if we see a latitude dependence, this is probably playing a role. Okay, yeah, and I think I'll skip that. I want to say something quickly about lensing. So we see plasma lensing. I gave one example before with the extreme scattering events due to something like Gaussian blobs, but this has also been seen from filaments in the Crab Nebula. So this is showing basically the pulse shape. This is pulse phase on the x-axis, and then epoch along the y-axis. And you're seeing the double pulse here, which is real, but you're also seeing echoes or images of those, a secondary image of that burst. And so that's a filament passing along the line of sight. And it's also amplifying the signal. So anyway, it's a well-established effect, and there's also a very nice analysis by Robert Main for a millisecond pulsar where the lensing is due to the evaporated gas from the companion in a black widow system. So it's well established, and basically if you have a Gaussian blob, you will have either at any given point along the x-axis here, you'll either see one image or three images. They can also be heavily boosted. So what struck me was that if you plug in modest numbers here for the size of the lens, let's say 100 AU, and a modest dispersion measure through the lens, only 7 or 10 or something, then the focal length becomes a gigaparsec. So that means that we would, like for those conditions, an FRB viewed through this lens would be focused heavily, and you could get a boost of 100 in that case. So I thought that was pretty striking. And also the clock is pretty striking here. So anyway, if you look at a Gaussian lens versus frequency and X, you get this kind of structure. So you have a caustic here with gains of, again, up to 100 or possibly more. You also have a trough where the gain is 10 to the minus 2 or even smaller. So you can have an FRB come and go by the passing along the line of sight of a filament or something like this. All right, you can also get spectral structure. So this is now showing the gain from just a simple Gaussian lens as a function of frequency. So you get these spikes and so forth, and which of these curves applies depends on the impact angle to the lens. So anyway, this may be playing a role in some of the spectral structure. We'll see. Okay, and then you can have a more complicated lens, like an astigmatic Gaussian lens, just slightly astigmatic. You get much more intricate looking causatic curves here. Okay, and I'll skip that. So this is my last slide. So there's some points that I didn't go through, but I would say FRB pulses are intrinsically, this goes to the discussion yesterday, they're intrinsically incoherent sums of coherent shot pulses. And so I think that I wanted to emphasize that because there was discussion about, well, are they intrinsically microseconds in duration or what have you, or can you make the millisecond type bursts? Can you produce those by propagation effects without producing the asymmetry from the multipath? And I don't think so. I think the millisecond widths for many of them are intrinsic. Okay, so the question is turbulence in host galaxies similar to the Milky Ways? Is scintillation and lensing important for surveys and selection effects? How much of the spectral structure is from caustics, or sometimes called optical catastrophes? And but then, and this may lead up to Andre's talk, is the role of high amplitude electromagnetic waves and nonlinear propagation through the circum-source medium. And then lastly, we talk about emission and propagation as if they're always separate. And I don't think that necessarily is the case, especially close in, where it may be difficult to draw the line here. So we can have mode coupling and mode conversion, adiabatic walking that Wenbin was talking about. And again, perhaps maser amplification of the incident radiation. So I'll finish with that.